Welcome, this is lecture number 25. In this lecture, we are going to talk about the overview of modeling technique and we are going to consider few motivating case studies. So, first we will discuss what are the objective of testing and validation in switch mode power converter, then need for modeling to predict transient and steady state performance, then primary modeling objective which can be categorized into three parts. That means, we need to predict, then we need to select the suitable control technique and then we have to design as well as we need to automate the process in order to meet certain requirement. Then we also want to see what is the model simplicity versus accuracy and model limits on control bandwidth, that also we will discuss. And finally, some small signal and large signal modeling technique and then their significance, okay, that also we will discuss. So, a DC-DC converter under test, and this is a diagram I am showing from Chroma, where it is just typical setup that we want to test a DC-DC converter, where the DC-DC converter can be a PMIC, where we can connect the external inductor capacitor, but the PMIC will have its own controller, its own switches, and we need to evaluate the performance of that IC. That means, what is its load transient performance and so on, what are the control logic. So, that means, here the objective that we will have a DC-DC converter, okay, and now this DC-DC converter will connect an input terminal, that means a supply, and will connect either electronic load or a load which can be a resistive load, because in electronic load it is very hard to do transient simulation when particularly if you go for low voltage high current, because the slew up process may not be much faster. So, we need to make a special load in order to test high slew rate load transient. And also we need an oscilloscope, right. In fact, there can be other devices like a measuring instrument, like we may need a digital multimeter, right. So, the oscilloscope we can actually observe various waveform of the oscilloscope, whether you want to see current, voltage, then you need also current probe, voltage probe. So, different probes are needed. Now, here I am showing a load transient test case of a boost converter under voltage mode control. So, here as a designer I have designed the boost converter, but I am not revealing. Suppose I am making this boost converter and I am making it as a commercial product, for example, okay. But now I want to sell it to another, like a customer, like how that power management industry they perceive that the industry want to design a converter and its controller, and which is designed based on their certain technique, and which I am not going to discuss now, because as we move forward we will see different modeling and controller design technique, and many of them are followed to design such converter. But now once suppose we bought an IC, this is a boost converter and we want to test in the laboratory that what is the performance. So, here I am showing a load transient performance. So, here we have made the converter and we are also testing whether it is meeting our requirement or not. So, this is under voltage mode control, and you can see that transient performance is not good because our switching frequency is 500 kilohertz, but it is taking almost kind of 0.2 millisecond, basically 200 microsecond, which means almost 100 cycles when there is a load change from 1 ampere to 4 ampere, and when it go from light load to high load, that means, but boost converter will see very soon that boost converter suffer from non-minimum phase behavior. So, we cannot increase the bandwidth of a boost converter drastically like a buck converter, because there is a physical constraint, and for the time being we are not going to discuss. So, here we have designed a 7 volt input and 12 volt output boost converter, and we are operating 400 kilohertz, not 500. So, 400 kilohertz switching frequency. Now, the question is, if we applied a 1 to 4 ampere load step, you can see this is the AC coupled output voltage. So, this is my AC coupled output voltage. So, we are getting some overshoot undershoot, right. So, it is undershoot is coming almost 0.5 volt because this division is 0.5 volt and this may be too large because 12 volt though, and current also have some overshoot because if you check that here to here there is certain overshoot in the current. But how can we predict that what would be my overshoot or undershoot, because we have designed this converter keeping in mind certain specification. But when you are testing, we need to check, correlate that whatever we have designed, are you going to meet or not. So, this is like a testing and validation, this process. In this case, the process is that we know the converter, we know the procedure of design and we have followed that procedure and we have obtained those controller gain as well as the control logic, voltage mode control, and we have made a closed loop control system and then we have applied a load step transient and this is a response. So, as a validation engineer, what we will see? We will find out whatever undershoot we are getting, is it matching with my specification? That means, I can design the converter either using frequency domain specification or time domain specification. Even though if you take a time domain specification, you need to correlate in frequency domain because most of the compensators are designed using frequency domain, where the time domain you have difficulty because there will be multiple poles and 0. In frequency domain, we have to will consider in terms of phase margin, bandwidth, crossover frequency and so on. So, we need to check whether the obtained performance is matching with my desired requirement or not. And in often you will find they may not match, they may match closely, and this mismatch can have there can be various reasons. That means, whether are you taking a suitable measuring step, that means are you taking the right step to measure. If you introduce more parasitic into your converter or in the process of measurement, then the measurement actual converter behavior is different and whatever you are measuring, that can also have some effect, because we need to set, you should not use a very long cable, and that we have discussed in lecture number 13. So, you have to be very careful about the setup. So, by following all the standard like a procedure, are we able to match our requirement or not? So, that means this poses a question, how do you match? Even if they mismatch, we need to find a solution. This is one way of looking at this problem. The other way, you have been given a converter with control, you do not know what type of control it is used, you know only it is voltage mode control, but you want to check whether whatever response you are getting, can you predict what kind of transfer function or what kind of compensator is used. So, in all these cases, we need some information about the system. That means, first of all, we need even the converter, we are only selecting the inductor capacitor value, right. Then we know about switching frequency. If you just zoom the waveform, here it is given at 400 kilohertz. Another scenario I am showing, here it is again a boost converter, the same load transient, but now it is under current mode control, and here we are using a large signal based control, not small signal. Even in current mode, your performance will be limited because of the right half plane 0, but here we have applied some large signal based tuning controller design, which we will discuss at the end of this course, and you could achieve the performance of the boost converter like a super fast. So, this is the fastest performance that you can achieve, and this is also known as time optimal control, time optimal performance. The performance that we achieve, that means your response time is the fastest, you cannot get anything better than this. But yes, this also comes with a price, your undershoot is large, this is a non-minimum phase. If you want to reduce the undershoot, then you have to put a limit, but we are not going to discuss this. So, what I am saying, this we have obtained using a closed loop control, but how did we arrive this closed loop control? Who said this? Can we obtain this performance by any like a trial and error method? No. So, we need to follow, that means we need to know something about the system, we need to know something about the model of the system, that means we need to develop some model. And we will soon find there is a fundamental difference between this approach and this approach. In this approach, we will view this design of the controller using transfer function, small signal model. And in this approach, your transfer function is not valid, we will see, because we are allowing the duty ratio to saturate. So, your perturb model is not valid because the perturbation is quite large and there is a duty ratio saturation. So, that means the small signal model even we are familiar with, even if we can find out that model is not applicable here. So, we need another level of modeling. Why? Because this model will find that this model is much simpler. You can apply the linear control system theory and the well known theories are there, and you can play with the transfer function with achieve desired Bayes-Mondy. There are different tool, MATLAB control system toolbox that can also be used. Okay, there are analytical technique. So, this actually you can represent using a linear system. But in this case, since actual converter is a switching converter, so here the linear model is not valid. And the fundamental difference is very obvious that the response is drastically improved, because here it was taking around hundreds, because it was taking around how much? It was like this much time, and it is like around 150 to 200 cycles, whereas here it is taking only a few cycles, maybe even 4, 5, 6 cycles or within 10 cycles. So, you can see a drastic improvement in the transient, more than 10 times faster. So, in the future power supply, we need more and more performance, and here it can be shown, in fact, we will show in the subsequent lecture. If such transient happen more frequently, for example, if you are driving an LED load where the LED is a dimmable LED and it is undergoing load transient more frequently, because the LED frequency has to be much faster so that our eye cannot perceive. And under such fast transient, if you can save energy by slewing out very fast, so you can also improve the efficiency, because the efficiency will not only be decided by steady state, this transient efficiency or the energy efficiency will also become important. So, that means we can improve the performance as well as efficiency, but at the cost of our linear model is not valid. So, we need to incorporate some nonlinear model here. That means, even though we try to do a modeling technique, we need to understand at what level of model we need, whether we need a very simple model, that is okay, it is reasonably easy, you can handle or you can deal with your very well rich tool design tool of control system, but you have a limit in the performance because it is a switching converter. But if you can go a little up, that means if you go somewhat up level, top level, where you incorporate the nonlinearity into that model, you can actually extract the performance up to the limit of the converter, because it is a switching converter. So, the question here what I am asking, there is a small signal based design, and in fact, this one of the objective of this course is to show that in future control we will see more large signal where we want to improve the performance by many fold. But we are not going to change the modulator, modulator remains same, okay, and we will show that controller current mode control will also structurally remain same, but the philosophy of design is different. So, you can improve very fast, but the question is how to predict response, how to predict this response and how to predict this response. And I said that this response, if you try to draw a line in between, so this can be predicted by a linear model, like there is an undershoot, overshoot like this, and it can very accurately predicted by linear model. In fact, in the subsequent lecture, I will show model matching. That means, whenever you design a converter, first we will design using small signal model, we will derive transfer function, we will design controller using our linear model, which are AC model, then we will get the AC transient response using that our linear model, then we will add the operating condition, and then we will compare with the actual switch simulation, and you will see something similar. The red line is the result obtained from linear model, and the actual switching converter is the blue traces, that we will compare in the subsequent lecture. Okay. But you will see this matching will start deviating when you try to increase the bandwidth of the controller. So, there is a band limit, model limit in the design. And if you want to go by this way, then how can you incorporate that information and how to predict this response? What is my recovery time? Can I analytically predict for a given step size? Can I design a suitable controller to achieve this kind of response? So, these are the questions that we are going to ask. Now, coming back to an open loop buck converter. So, we talked about a closed loop boost converter. In open loop buck converter, if you take a synchronous one, then we know we can take the MOSFET, right, high side, low side MOSFET, and we need to provide dead time for a real MOSFET. But here the dead times are much smaller than the total time period. So, here for the time being we are neglecting. Also the dynamic of the MOSFET, because MOSFET will also have turn on turn off process, but if you look at the dynamics of the converter, that means compared to the dynamics of the switches, so these are much faster than the dynamics of the inductor and capacitor. So, it can be framed into a singular, we can apply singular perturbation theory, where the two systems have difference in their time or dynamic. That means one is very fast and another is very slow. So, the faster one will decay very quickly and then it will be primarily dominated by the slower one, and that is exactly happen. And under such consideration, we can ignore the dynamics of the MOSFET, because once we derive small signal model, then we will see the MOSFET dynamics are so fast. So, the small signal model does not require, you do not need to incorporate that model, as long as your rise time fall times are only a small fraction of the time period. So, we are taking just a single switch and we are taking the parasitic, that means the parasitic component rather than the dynamic component. So, this can be replaced by a parasitic model of a synchronous buck converter. Now, I want to show, in fact, this result I have shown in lecture number 13, where I have simulated a synchronous buck converter with an open loop duty ratio, where my input is 12 volt and my Vref desired was 1 volt. So, I set my duty ratio is 1 by 12, Vref by Vin. But if it is an ideal buck converter, no parasitic drop, then before and after load transient, the average value is setting at 1 volt, it is perfectly 1 volt. Whereas, in the practical case, it is not going to 1 volt. So, it is less than 1 volt. And also, there is an overshoot undershoot in this process, which also we need to identify. So, our question is that, can we analytically predict what will be my practical voltage operating point for any load and input voltage condition? Can we practically predict this undershoot and overshoot even for open loop as well as closed loop converter? So, these are the questions which motivate us, why should we go for modeling technique? Okay? So, how to achieve this if we want to achieve? Now, the next question will ask, how can we achieve 1 volt output even for a practical converter? Okay? Now, I am showing another case, reference transient in a synchronous buck converter under voltage mode control. So, here again the buck converter is running under voltage mode control, and I am not saying what kind of compensator I am using, but here it is well known that I am using a type 3 compensator, and we will soon discuss this compensator structure as well as its design for both buck and boost converter. But for this time being, what I am going to discuss, so the red color trace, the red one, which is the response from small signal model. Though we have not discovered small signal model, but assume that you can derive a linear transfer function out of a DC-DC converter by suitably applying averaging technique as well as the perturbation theory. And the blue one is actually our switch simulation. It is coming from actual switch simulation. And the red one, which is obtained by, because it is under closed loop control and we want to change the output voltage from 1 volt to 1.1 volt. Okay? And here we have designed a compensator by setting a bandwidth crossover frequency of FSW by 10, that means 1/10 of the switching frequency. And then we saw the response obtained from the closed loop transfer function of the buck converter using transfer function, and that is the AC response. Then we added the DC. It is almost closely matching with that of the switch simulation in the average sense. So, that means they are matching. That means which says that we can develop model which can more or less capture the behavior of the transient response of the DC-DC converter, and we can predict what is the overshoot, undershoot, what will be my settling time, and this thing can be predicted simply from a linear model without going to switching converter. So, that means if you can develop such model, we can predict the response by without running the actual switching converter, and from that process we can set the controller in order to achieve some desired performance, so that we can actually test the converter. The next question, how can we predict the steady state and transient behavior? Here we have predicted, as we know that, but I am opening this question and asking how to develop this model, so that we can get the red trace from our model. How can we develop? The next question, I have increased now the bandwidth. I have used the type 3 compensator and I have designed the compensator to achieve my crossover frequency FSW by 5, that means 1/5 of the switching frequency. And you see the response due to our small signal model, and this is actual switch simulation, they are drastically different. That means even though you are able to model it, even though you are able to design it, and from the linear design you obtain this response in order to improve the transient performance, but when you actually plug in, because this after this design essentially we are designing a compensator, and which is a type 3 compensator, right. So, what we are doing? We are designing this type 3 compensator by considering a small signal model, assuming that you have the model with you. But if you design the compensator by the model and your model shows this response, but the same compensator if you apply, if you consider in actual switching converter, they are largely, it is deviating. That means this model is of no use, because if you cannot predict accurately with your switch simulation and your model response, then this model cannot be used or should not be used, because your actual response can deviate significantly, and as a result there is no point of validation. So, that means this will also pose another question. Even though you are able to develop a model, so there will be certain restriction of the model. We cannot use that model for the entire range of the bandwidth. That means we cannot increase the bandwidth drastically. Though this model is simple, this model I will show you it is simple, but this model is not effective for when you want to improve the performance. That means this motivates us, if you want to do modeling, if you want to start with a very simple model that is reasonable, you can design the controller up to certain performance, but if you want to achieve faster performance, you should not say that I cannot design, because then we should look for an alternative model, because it is a switching converter. It is capable to provide much faster response than what can be achieved using linear model. So, that means you need to find the next level of model which can be advanced version in order to speed up the response. So, the small signal model does not work, and we need to find some alternative model. Again we are talking about load transient response under current mode control, and you can see the red trace, again it is coming from small signal model, and the blue trace is coming from our switch simulation. And I will show you this small signal model under current mode control is very simple, it is just a fast order model, but it reasonably captures the behavior. Even in I will say it is reasonably correct, except for this portion which it cannot capture, otherwise it is fine. It is capturing the behavior of the converter, closed loop behavior, both linear model and switch simulation. So, that means it motivates us that there some model exist and we should try it out which can match our closed loop response of the model can match with the actual switch simulation. So, it is matches fine with 12 volt input. Now, if we operate at 3 volt for 1 volt output under closed loop, model seems like matching fine, like it looks like in average sense it is matching fine, but if you zoom this portion and corresponding inductor current I am showing, this is my inductor current, you will find subharmonic oscillation. That means, in our common sense, I will not say it is a stable behavior. In average sense, yes, it is a stable behavior, and that is why the model is predicting average behavior. But this model is unable to capture the subharmonic instability, because if you design a model, if you obtain a model, if you design a controller and you say that okay, I can achieve this much undershoot, my settling time is this much, so it is perfectly fine. But when you implement the controller, in average sense it works really fine, but you end up with this kind of scenario in actual converter behavior, which is not acceptable, because your ripple has increased drastically, your RMS current will increase drastically, as a result conduction will also increase, and you have a subharmonic component where you will have a sufficient power in the subharmonic level, and that will really create trouble in your filter design. Okay? That means, this model what we have developed, small signal model, this model we cannot go for very high bandwidth, we saw there is a significant deviation. This model cannot be used to capture subharmonic instability, but there are technique I will discuss in the modeling technique of current mode control, which can be used to capture this subharmonic instability, at least to identify where it can happen, okay, by incorporating the sampling effect into the current loop, current mode control small signal model, but in standard traditional model cannot predict it. So, then this model is also not very useful, because it is unable to capture this first scale instability. That means, this gives us the motivation. It is clear that modeling is needed to accurately predict the transient and the steady state behavior under both open and closed loop, because if you can first check the open loop, because ultimately our objective is to design a voltage source, and if you recall in lecture number 13, if we want to make a very tightly regulated voltage source with a high bandwidth, that means our objective is to go close to an ideal voltage source within a range of current, then we should have a very high end controller, and for that we need really to have a model, that means to predict. Also, the steady state behavior, the model should also capture whether there is a subharmonic or not. Then we should, the next task, once we are motivated to get a model, now we suppose we are trying to investigate what kind of models are available and why so many modeling techniques are there. Because I told you, it starts with a simple model. You can have a very simple model which can predict up to certain behavior, then you should be happy. But if you want to push the performance further, then that model is not useful, then you have to go for next level of modeling, where your complexity of the model will increase. Once we have the model, then we need to select the suitable control method, and we need to, depending upon the application requirement. So, if you need a current mode control, for example, in for let us say voltage regulator module, multi-phase, then it is better to go for current mode, and then we need to implement, we need to consider such model and to design a very high bandwidth current controller. The next third objective is, once we have such model and once we identify the control method, the next task is to devise some suitable design guideline. How can we develop the steps to design controller in order to achieve fast transient and the stable response, and which will can also ensure subharmonic instability will not happen, and the transient performance actually should match with your switch simulation and actual the model you obtain. Then the next task, once you have the right model, and we can also optimize we can improve performance, improve efficiency, then we can create a block, that means kind of a library for any given inductor capacitor. That means if I have discussed in lecture number I think probably 13, where many industry have their own called designer tool, and the objective of this designer tool is an automated tool where you need to plug in lot of model there in that tool, and that will ask for what is your input voltage, output voltage specification, what is your load current. Then using that information, it will first select what is my inductor value, capacitor value, what will be my switching frequency. Then it will try to correlate in different industry, will try to correlate what is their existing product close to that, and what are the range of product that can meet certain input output voltage specification and load specification. Then it will give you different variant. Okay, you have like a IC number 1, IC number 2, which can meet all these specification, but each of them has certain bill of material. That means some of them are using higher switching frequency, some of them using current mode control, some of them using voltage mode control, because if you want to, because you have not given any specification of the transient response. Once you start adding more and more advanced feature, then it will filter out and probably it will try to search the right suitable product which can meet your transient specification. And it may so happen, if your transient spec is very stringent, you may not find any product at all. So then you need to find your own solution, and that is how the technology development happens. So that means this automated tool is very important to develop, so that your new control technique comes in, or even for existing control technique we need not to spend lot of time in designing from the scratch. So you should develop the model, and if you just plug in, the model should tell what is my compensator gain. In fact, in this course, whenever we will go for design, I will demonstrate some MATLAB.m file, where if you specify some gain margin, phase margin, then or even if you specify some phase margin and control bandwidth, then it will give us what are the compensator gain for a given inductor, capacitor and voltage, input voltage, output voltage. Okay, and then you can actually obtain the compensator, and you can plug in, and you can also match the response of the model as well as the switch simulation. So that means this step is also very important. It will try to automate, so you do not have to spend time again and again writing code matching. So in one code it should be generic, which will ask for some specification, which should take the values from some parameter file. Then understanding output impedance. So output impedance gives us the flavor of load transient response. That means we can predict the load transient response by looking at the output impedance. Okay. So that means how does it help? It characterizes if there is a load step change, is there any DC shift? In fact, this we have discussed using a case study in lecture 13, when we talk about a practical voltage source. So a practical voltage source, if there is a DC shift, which indicate there is an internal resistance, DC resistance, right? So this is a steady state effect. Then if there is a discrete jump, very high frequency, then we can also predict what is the real component of the Z0, which will cause the discrete jump, high frequency jump. And then undershoot, overshoot can be predicted by the AC component or the frequency dependent term. That means if we can get the model of the output impedance, then for an open loop converter for example, then we can predict very accurately the transient response of the converter when you apply load step. That means this will give us, without going into test and validation, first you can say that if I apply 10 ampere load step, my undershoot is this, and which is not acceptable. How to identify output impedance? So we have to devise under test. That means this is what, if you go to any experimental validation, if you have a converter, you can inject since you have pulsating load, and looking at the overshoot, undershoot, you can try to match the get the output impedance. Okay. So this step we will discuss that how to get the output impedance. But when you talk about steady state, when there is no load step transient, the converter should first reach to steady state. That means we are talking about this condition. Then we apply a load step transient at t equal to T0, this is my T0, okay. And at that time there will be a direct jump in the output voltage which is not visible here, but there was output voltage suddenly jump, again it will further decrease. So, this jump is basically due to the combination of R and RC. So, if there is no resistive load, it is purely by RC high frequency jump, and which cannot be avoided if your ESR is fixed. And you know what the designer is to do, instead of using a one output capacitor, generally multiple output capacitors are used to reduce the effective ESR. So, ESR can be identified, then if you see the steady state difference, then you can get the DC output impedance, and you can also find out some AC output impedance by measuring overshoot, undershoot, and that means we need a model of the output impedance, okay. So, the model should be, now it may so happen whatever model, that means you did a practical test of a converter and you try to derive, because the converter is nothing is known inside except for inductor capacitor, right. So, you need to obtain the closed loop output impedance expression. Then what we to do? We may not be able to model everything. So, from the measured response, if we want to match, so if some information of the converter, for example, in the buck converter, we know output side there is an inductor, capacitor. So, we know the circuit and we can write the, we can derive the model and try to match, and that is the white box model. When the model is available, and then you can try to derive, try to match the model or identify the exact parameter of the model from the measured data. But it may so happen sometime the system is partially known, because there are a lot of unmodeled dynamics, for example, ESL effect, parasitic effect, in the trace resistance effect, then there can be some additional delay which may not be directly measurable, but if the partial information of the model is available, then we can use something like a gray box model for identification. And such model identifications are very important for future power converter, where we are talking about digital twin, where there can be automated tool, and if you just from the run time of the system, because there are a lot of online controller tuning method, there are very highly cited papers are available, which the tuning using digital platform can be carried out by simply identifying the model in real time or measuring some phase margin, as well as some parameter in real time, and you can tune the controller, okay. Because when the load changes, you need to know what is the new load condition. So, from the identification method we can extract that. Now, the next question, we are sure that we need a model, but what level of accuracy we need it. Now, if we go back to a periodic signal Q of t, and if we apply Fourier series, then because it is a periodic signal, right, under steady state it is time period is fixed. So, we can write this Qt, the gate signal, and we can write the synthesis equation as well as the analysis equation, and you will find there will be a DC component corresponding to analysis equation. So, if you go to the power spectral density, which can be obtained from the Parseval's theorem, and the power spectral density can be written by this power spectral density simply d square into the sinc function square, okay. So, I am not going into derivation, but this can be derived, the power spectral density. Next, this power spectral density gives us that what is the power content at different harmonics, that means at k equal to 0. So, this is f by f0, where f0 is our fundamental component, which is nothing but our switching frequency in this case, and 0 component is the DC component, that means this corresponds to our duty ratio d into t, right, duty ratio, and that corresponding power. Now, in a DC-DC converter, if Qd equal to D0, it only gives us the DC quantity. Then if you find out D1, what is the component of the duty ratio or the Q for the fundamental frequency of the switching frequency, you can also find out the higher harmonic. So, that means we can extract the power corresponding to different component, but you will eventually find the maximum power will retain at the DC component, which is the fixed duty ratio. That means again DC-DC converter is driven by a train of periodic pulses consisting of a DC component and a fundamental component and its associated harmonics, provided that there is no subharmonic oscillation. If there is subharmonic, suppose if you take the example of, this is a periodic waveform I am just drawing, but for the same time period, if you draw another waveform which is something like this, it may be something like this. So, which is like this. Yeah. So, this is my subharmonic component. Okay. So, in this component you will see for the red color there will be a peak here, because as if it is repeating, this time period is t, this time period is t. So, as if it is repeating after 2 time periods. So, it will have a component of FSW by 2 and it will have a component here. So, subharmonic you will have a power component, power spectral density at subharmonic level. Now, the question is how can you obtain an approximate linear time model, linear time invariant model, LTI model, because whatever we have model using a linear model, I think the response using a linear model I have demonstrated. How can you obtain that? So, you can use a state space model and then you can apply a state space averaging. Then you can use a circuit behavior and apply circuit averaging technique. Then you can use an average switch model and applying averaging. Then you can use a state space model and apply generalized averaging, and there are state space model, apply discrete time model, and there are many other options are available. So, I will take just a glimpse of state space model. So, if you take a synchronous buck converter, if you take the switch configuration 1, then you can write and switch configuration 2, and if you take the state, one state as the inductor current, that means I am taking state 1 is my inductor current and state 2 is my capacitor voltage, which is here. Okay, and then you can write x1 dot, x2 dot, and their output y I am taking V0, that is my output. So, you can write the state space model for 2 different switch configuration, that means sub interval 1 when the switch is on, and then you can write the same equation for sub interval 2 when the switch is off. But we are keeping the same state variable for throughout. Next, overall state space model, it will have 2 components. So, this kind of structure is called switch linear system. For within a switching interval, it is a linear system, but 2 linear systems are combined by means of switching. So, their A matrix are more or less common except for this difference, but their B matrix are drastically different, it is a null matrix, and C matrix are common for this converter. But if you take a boost converter, A1, A2 are drastically different, they are totally different, but B1, B2 will be identical, C1, C2 will be different. Okay. So, that means for any generic converter, you can assume that for every sector of the sub interval, you will get A1 AJ, Vj, and correspondingly you will get the output voltage expression. Then once you get the switch linear model, if there are only 2 switching event like switch on and switch off, and switch on happen during the d into t time and switch off happen during 1 minus d into t time. So, the averaging technique, you can standard averaging technique, you can simply average them d times into that average state and then d times the V in, and after averaging, because the original model if you go, it is basically a switch linear model, so nonlinear model with switching nonlinearity, where we cannot apply linearization because it has discontinuous nonlinearity. But once you apply averaging, then it becomes a smooth vector field D. It is a nonlinear function, it is a nonlinear function of d x V in, but this nonlinear function is continuously differentiable, it satisfies the Lipschitz continuity. Then we can apply perturbation and we can find out the equilibrium point, and you can apply you can get the linearized model simply by applying Taylor series linearization. Then we can, and in fact I am just going a little bit fast because we will discuss in detail in the next lecture about the state space averaging method. And if you go to circuit averaging method, in the earlier method, whatever we get this model, it is more like a mathematical viewpoint, which is good, which is very informative, but as a circuit designer, it has less intuitive understanding of the circuit. The other thing, in this converter, we have taken this model. Okay. Suppose we add a parasitic inductance here, which is called ESL. Then the whole state space model dimension will increase, because it is now third order, because there is an energy storing element. As a result, you have to increase the order of the state by 1. So, that means again, if you consider an input filter here, suppose you consider an input filter here. So, input filter has energy storing element, it will also have dynamics. So, that means when you write the overall equation in state space representation, you have to rewrite the whole equation. That means you rewrite state space equation, you have to rewrite the state space equation whenever you add any component also. That means if you even add a small resistance or apart from energy storing element, but even if we add a resistance, only the coefficient of the A matrix will change, but if we add an energy storing element, the dimension of the state space will change. So, one of the major drawback of state space model is that once you add some circuit element, then you have to rewrite the equation. So, it is kind of a lengthy process writing the equation, rewriting. So, you want a usable solution where we do not want to repeat this derivation process even if we add some component, and that is where the circuit averaging comes into picture. So, that means equivalent circuit model. That means by means of circuit averaging, we will discuss if we obtain this equivalent circuit model. Now, if we add an ESL, this will remain same, this model is perfectly valid. So, the order of this model will increase by 1, but you do not need to rederive this model from starting from here. You can simply add this inductor. Even if you consider an input filter, this model is also fine, because you can add some more parasitic left side and right side, it will work fine, as long as there are certain restriction. If you go to equivalent circuit model, that means average switch model, if you can satisfy that requirement, then this model is more generic and it can accommodate more more circuit element, but still the model is applicable. And for the same parasitic inductor, capacitor, everything, the SA model, that means the transfer function using circuit average model and the state space model, they are identical. So, that means the state space model can be obtained from mathematical equation, which is also fine, but this method can give more physical insight in terms of output impedance, in terms of input impedance, in terms of audio susceptibility, control to output transfer function. So, it will give more physical insight. And the last one, when we talk about subharmonic instability, because we talk about there can be this kind of current scenario which cannot be captured by a small signal model, and then we need to go for discrete time model, and if we can find out under what condition this stable periodic behavior is lost. That means stable periodic behavior is lost and is going to instability, that can be predicted. And if it further go into subharmonic instability, and there is a nonlinear dynamics, that in that context we can go into nonlinear dynamics and check what kind of behavior we can achieve when it goes into instability, subharmonic instability, what type of behavior can be possible. So, that means this discrete time model, it also uses state space model, okay, and AB matrix, that means whatever you use in state space, the same state space model will be required here, but you need to find the solution of the state space model, okay. And this term is particularly very important, because if you want to get the solution of the state space equation, there are multiple techniques to solve to get an analytical form, but I am not going to discuss this technique because this will be somewhat advanced, and this may be in future any digital control can be offered, then this can be considered or discussed in detail. But for the time being, just for introduction, the discrete time model can be derived and this can accurately capture all kind of stability. But as you can see, this is mathematically complex system model. So, you should use only when you want to go and investigate such kind of instability. But as long as if you ensure by a simplified way that there is no subharmonic instability, and if you want to operate at a lower bandwidth of the controller, then it is reasonable to go with a standard small signal model. And here also you can obtain the small signal model from the discrete time model. In fact, majority of the digital controller we use discrete time model directly to accurately design the controller. But in analog control, the small signal linear continuous time models are still popular. So, the overview of the modeling technique we can divide into two parts: continuous time modeling and discrete time modeling. Then the continuous time modeling, we can have a state space averaging, circuit averaging technique, fast analytical technique, average switch model. We also can have a generalized averaging technique, singular perturbation theory can be applied, okay, 3-terminal model. So, all these models have been developed and they have been well reported in the literature, and harmonic balance method can also be used, which uses describing function method. And also the Floquet theory is a very powerful tool which also captures the discontinuity during the switching event using Filipov method, and also the trajectory sensitivity analysis can be used in order to get more accurate continuous time model. And the discrete time model, I already told, it is a very accurate model, but majority of these models are slightly complicated compared to the traditional model, particularly when you go for like a Floquet theory, harmonic balance. These are slightly complicated, but these techniques are more accurate than this technique. Okay? So, this can gives more information, but when you go to discrete time modeling, even it is more complex because of this solution of the matrix, writing matrix equation. So, we need to deal with different modeling technique. So, to start with, in the subsequent lecture, we will primarily consider these two techniques, particularly using average switch model. So, these are the technique that we will consider extensively and we develop small signal model. This will give you a lot of physical insight, okay, and we will primarily consider equivalent circuit model. That means, the equivalent circuit model, this can be derived either by circuit averaging technique, this can be derived even using average switch model, this can even be constructed from the state space averaging model. But if you can represent in terms of an equivalent circuit, then you will get a lot of insight in terms of impedance, in terms of control to output transfer function and so on, which will give you a lot of physical insight, design insight. So, summary, we have discussed about different difference between ideal and practical converter. We have discussed in detail about the objective and motivation of mathematical modeling. We have briefly discussed about state space modeling and switch configuration. We briefly discussed about circuit averaging technique, and we have also discussed about various overview of various modeling techniques. So, with this I want to finish it here. Thank you very much.